I'm an independent consultant, and I'm working with a number of customers in several projects, and I thought that the session today would be a lot about diameter signaling, as it has been many other years. So I wanted to review with you a couple of topics that I thought would not be spoken about today, although I have to say most of them have been at least mentioned. So I wanted to touch on these 6 topics, and I think mobile edge computing is the only one that has not been mentioned, but intrinsic, I think the concept was there in one presentation at least. So the perspective from which I want to talk is from the core network, and with the core network I mean the EPC. Because that's the area where I know myself best and where I'm expert. On the other topics I have been involved in the projects, and I'm just going to explain a bit, okay, what is this technology and how does it affect signaling. Many of these are emerging technologies, so we don't see the full thing right now there. So what I'm going to take is from design thinking, the approach of look at the extreme use cases. So I'm gonna choose one of the extreme use cases to see, okay, how does this technology affect signaling. So let's start with NFV. I think we haven't seen this picture yet today, although in the Ericsson presentation there was a variation of it. You know it, or I guess most of you do know it, and there was a time in which every presentation would have one of these there. So basically it's the ETSI NFV diagram, and I think it was also mentioned by Oracle today previously that we have 3 layers of management and orchestration, and you know that's one is needed for the infrastructure, the other for the applications, and the other for the services. And the EPC is actually inside the virtual network functions area. And how does NFV affect signaling? How does it affect the EPC? Well, let's have a look at what are the effects that NFV has into the network. And I like the first one. That's the one I'm really interested in, scaling down. Because scaling horizontally or vertically, up or out, that was possible already before. But the scaling in, actually, yeah, scaling in, so having micro deployments, it is something new that brings an interesting perspective. And I think it was in the presentation from Ericsson, so as you see, most of the topics have been mentioned. There has been at least mentioning 2 of the effects, and they are the effects that I wanted to highlight here as well. So I call it verticalization of the NFV core network, but it's now called slicing, yeah, and we had it like that in the Ericsson presentation, and it means you can have core networks for different applications, or in the extreme use case, because I want to take these to the extremes to see how does NFV affect signaling. What we can have is a core network for each subscriber, because we can have really small core networks, and that was mentioned also by Ericsson. That would be one of the extreme use cases. So what does this mean? Well, if we look inside, what we have there is the complete EPC, but it's a micro EPC. So the signaling topics that interest us, like security, policy, charging, they are going to be, they're not going to be a problem. There's not going to be a signaling storm into this micro EPC. There's not going to be security issues, because at the end it would only affect one user, so it will be a very, very, very unimportant security issue. But the focus, we have to shift the focus to the management and orchestration. That's where the signaling, because this is also control plane, deploying all these core networks, maybe on demand. When a user attaches, we will deploy his core network, if that were possible. But that's a possibility, let's say, of an extreme use case. But then what we're going to have is a lot of control plane and a lot of signaling for the management and orchestration of these core networks. So that's let's say, the perverse effect of NFV into signaling, that we add signaling on the management and orchestration. If we look at SDN, which nowadays we don't separate NFV from SDN, they come together. But let's look a bit separated, because SDN has a broader applicability than NFV. So if we look at SDN, we have SDN is several things. So one of the things that SDN is the separation of control plane from data plane. Then we have a centralized SDN controller that can configure and control several switches or all the switches. Switches, they could be also gateways. And then the possibility of deciding that each flow in the network will take a different route, even if it's for the same subscriber or for the same service. Ideally not. Ideally it's for different subscribers and different services, and that's the reason why you're going to take it through a different service function chain, which would be the SDN name of this topic. So what would be the stream use case of SDN? Well, the stream use case is that we have to configure each flow that the user has, that all users have. And of course, this means a huge amount of signaling, because whether it's OpenFlow or it's RESTconf or it's NetConf or it's whatever, it doesn't matter. This is signaling overhead into the network with SDN. And SDN networks, if we apply a lot of SDN, they become less predictable. Who's going to dimension this? Well, we are going to have to do it based on automated procedures that are going to require as well more signaling to measure dynamically the resources that we are using, and whether this switch has now resources available or not to handle this traffic, or we have to route it through somewhere else, to forward it to somewhere else. So this, another perverse effect from SDN, more signaling. If we have a look at mobile edge computing is about improving the user experience, reducing the round trip times. So what we would have in the chain is usually the data has to go all the way through the core to the services and come back. That takes a lot of time. But what mobile edge computing brings, and typically the scenario is that you bring services catching into the edge, into the radio network. And that could be for content or even also for DNS queries. And with this way, you reduce the round trip time, because of course the DNS query doesn't have to go to the main DNS server, but it can be cached there. And there are several solutions from vendors available today on this area. So what is the extreme use case for MEC? Well, what if instead of just pushing the services, we also push the core into the edge? And this is possible, and there are applications and scenarios where this is very interesting. For example, we have seen today small cells, and there was mentioned an enterprise gateway on the small cells network. Well, that's pushing the core into the edge. And there are other scenarios. I've been working with in a project that are military and public safety applications where you want to have more resilient, decentralized networks, and there are standards of IETF for this. So the only problem is, what do you do with mobility? Where do you put your anchor for mobility? Well, if in certain scenarios where you don't have to scale to millions of users, you might have an SDN solution for this. But this requires, again, more management and orchestration and SDN control in order to provide mobility. In some use cases, you don't need mobility at all. If we're talking about IoT sensors, why not have the core at the edge? Because the sensors are not going to move in many cases. Or they're going to move only within a tracking area, so you can find a place to deploy the complete core, which is near to the edge and provides less latency and less signaling towards the core network, to the centralized core network, let's call it like that. CRAN has been part of the presentation of the Small Cells Forum, so I think we are now all experts on CRAN, we know what it means. Basically, that's the node B with the control plane and the user plane depicted. CRAN is about splitting it into two units, so the radio remote unit, the remote radio unit, and the baseband unit. And there are two things which are important, and they have been touched upon in the Small Cells Forum presentation, but I think it was not mentioned why operators want to do this. And the reason is because you want to put the baseband unit in the cloud. And why do you want to put it in the cloud? It's not to reduce cost on hardware. It's what costs a lot of money is to send someone to the remote areas or to where the radio is to solve something or to do an upgrade or to modify something. That is costing the operators a lot of money if they have to go to each cell, to each node B installation in order to change something. But if you have all the processing, which by the way is IP based, in the cloud, then this is really, really cheap and instantaneous, and it's much more convenient. There are two problems with CRAN. One of the problems is that cylinder there, which tries to represent the front hole. The front hole is this new entity that appears between the radio remote head and the baseband unit. And depending where the split is, this was presented before in the small cell forum presentation, depending where you put the split for CRAN, you will need a very good transport network and a front haul that has a lot of capacity and very low latency. Depending where you move this split, if you move higher on the layer, so not level 1 or physical layer, but in the MAC, you have less stringent requirements. The other question is about the MAC. Where do you split? So, I mean, no one is going to split on physical because putting CPRI on the fiber, it's really doesn't make sense from a business perspective. So you're going to split on the MAC layer, and there's a lot of studies and research activities in this area where to split in MAC layer, and probably we're going to see different proprietary implementations of that. I'm not caring about that because I'm caring about the core and the signaling. What is the extreme use case? Well, the extreme use case is something that I'm seeing in a European funded project that one of my customers is working at, which is called 5G Crosshaul. And it's basically mixing Cloud RAN with SDN. And what they say is, okay, we're going to have Cloud RAN, but we're going to have also an SDN controller. And in the front haul, we're going to have some forwarding elements which also have compute capabilities. And they're, depending on the scenario, what is going on dynamically in the network, we are going to change the baseband unit and move it nearer to the edge, because maybe we need less latency, because that's another topic. Cloud RAN adds latency. Worst case, you need a very big baseband unit deployed at the E node B, and at the end is a normal E node B. What is what happens? Well, backhaul and front haul are no longer different. With this approach, what we are redesigning as part of this European project is new protocols and a new frame format that can support both packets from backhaul and front haul. Because depending on the dynamic capabilities or the dynamic congestion of the network, we might decide to convert a front haul into a backhaul or the other way around. So that's very SDN. It's a bit visionary, but it's an extreme use case. And of course, it adds signaling. So right now, except mobile edge computing, I haven't seen any improvement on the signaling, and it's not getting better. So IoT has been mentioned a couple of times today. There has not been mentioned much about low power wide area network protocols. There are new radios technologies there, like Sigfox and LoRa. And the reason why we have new radios is because we have these requirements that are very difficult to fit in the 3GPP, let's say, portfolio of radio networks. 2G, well, is 2G an option? Well, it's not ideal anyway. The key thing, well, 3GPP is now catching up. I think there are two let's say, competing standardization activities, one led by Huawei and China Mobile, the other one coming from more for Ericsson. And the problem is Sigfox is there today, LoRa is going to be tomorrow. The 3GPP standards, let's see, maybe 2 years. So if you are really serious about IoT, the 3GPP standards might not be an option. So what would be the extreme use case? Well, for me, the extreme use case is that we have to go back to this picture, which I guess you know, it's the non-3GPP access. So it looks like the previous one, but the core network I had was only with 3GPP access. I have then to support non-3GPP access. And the reason why for IoT I would need this is because there are use cases that don't match the traffic profiles that are supported by these new radio technologies. So Sigfox and LoRa have very specific applicability scenarios for sensors, providing very low throughput and things like that. But in a real IoT scenario, like agriculture or e-health or many scenarios, they are not just sensors, they're also actuators, and there might be video applications that you need to activate at a certain moment. So from the application perspective, let's say over the top, to look into the network, I don't want to care how my IoT devices are connected into the network. So I need the core network to solve that for me. to give me a layer that integrates these new radio technologies with LTE or 2G, with all technologies, and I just want to care about IP and communicating my data to my sensors or my actuators, my devices. I don't want to care about all this radio stuff. And we see that our operators, at least in Europe, going to deploy LoRa networks and integrate them with LTE networks because there are opportunities around this. That's becoming interesting, but of course it's not simplifying signaling. It's just making it more intensive in the core network and let's say not helping us. So we go for 5G. No one wants to define 5G, but actually there's the NGMN white paper that everyone, when we talk about 5G, goes back to. And there was recently, I think it was here in Texas, in Phoenix, the meeting from 3GPP on the radio area that they decided, okay, we're going to need a new radio also for 5G. Of course, LTE stays, of course, Wi-Fi is going to be important, but we're going to need a new radio. And that's already agreed. So 5G is going to be multi-access, it's going to have higher reliability. It's not that current networks are not reliable, but what we expect from 5G is that it's going to be completely reliable. And lower latency, which gets always a lot of press, it's a challenge. And then new network topologies. No one knows exactly what we are talking about here, but it could be that we are mixing some of the stuff I mentioned before into a new architecture. And then NFV and SDN, it's by default. So 5G is by default virtualized and software defined. There's no other option. This is not going away. So what would be the extreme use case by 5G? Well, I think that's still to be seen, but there, with conversations with two operators, and actually AT&T has made public presentations about this, they are looking on a new core network, and they're looking to a core network that is going to be multi-access, where the radio stuff is going to be on the radio. So I don't want to have an MME part of my core network. Put it on your radio because it's something that you need for LTE, but I don't need it for Wi-Fi, or I don't need it for LoRa, or for millimeter wave radios that will come. Then we want a fully SDN core network, which is based on simple switches, not so simple. Maybe they're going to need to support things like, well, of course, GTP, if we stay with GTP for mobility, and maybe NSH as encapsulation for this service function chaining, which is, let's say, SDN detail. And then one thing which is interesting is that there's a layer of SDN control which is doing something that usually you don't see in SDN control. So what the AT&T is presented that they want to support in this SDN control layer is charging, security, and policy and quality of service. This is usually what the core network was doing. If we add mobility, that's a core network. Why don't they put mobility there? Is they say mobility is on demand. Not all devices that I will have in my network need mobility, or they don't need the complete mobility. So it's based, let's say, where most of their traffic is going. GTP adds a lot of overhead and a lot of signaling, which is only needed if the user is going to move, and if it's going to move from one cell to another, or if it's going to move from one tracking area to another. And most of the time that doesn't happen. So why have a core network, and why put this overhead, why put this cost into all the traffic? For example, for machine-to-machine and IoT, we need really a very cost-effective core network. And maybe those devices are not moving. So why put them on GTP? Why add all that overhead? So that's why they say mobility is on demand, and that's why I depicted the anchor, the mobility anchor, as an optional value-added service that you could chain to from the classifier or the switch. These are, let's say, SDN concepts, which are not very important right now. Another opportunity or another possibility here is to have decentralized as well. So really mobile edge computing, going to say, okay, for some accesses I might have this central switch or gateway at the edge. And we saw that also on the small cell forum with the enterprise gateway for small cells. Part of the traffic could be offloaded there. doesn't have to go through the main core network. If it's not going to be charged or it's not going to be offered quality of service because it's on Wi-Fi without support for quality of service, then why send it to the core network? Why does the PCRF need to know? Here, of course, there's no PCRF. It's the SDN controller doing that. But what could happen is that the SDN controller is actually talking a GX interface to a PCRF or a GY interface to the charging system. The SDN controller may be speaking S6A for the authentication to what's the subscriber database that I have there. And there's, of course, a management and orchestration because all of this is going to be NFV based. So we still have that. So to recap, I had an idea of, let's say, protocols. Of course, IPv6 will be there. It's not that important what happens on the other interfaces, whether it's OpenFlow or RESTConf or something else. For the SDN control to the switches, it's not relevant. In the same way, whether the switch or classifier is going to use NSH or something else, I don't know, maybe VXLAN or whatever. I mean, VXLAN wouldn't be applicable, but something in this direction to let's say, chain these services to build a complete end-to-end user experience, that's irrelevant. That's just a matter of technology, so to say. So as a summary, I try to, let's say, qualify a bit which of these technologies is helping us to have less signaling in the network. I mean, maybe it's controversial. Maybe the question is wrongly formulated. Maybe we don't want to have less signaling, but I assume that the operators would prefer to have less signaling because less signaling means less problems. So none of these technologies except mobile edge computing, when you don't take it to the extreme of having the core network at the edge, and you don't take it to the extreme to try to support mobility on that and keeping the IP addresses, which is very complex, mobile edge computing would help you to reduce signaling, but all of the other technologies don't. So I think it needs to be added into 5G to have as a requirement to reduce the signaling, and that's what, well, that's how I take what AT&T is presenting. They are doing it with very provocative, let's say, titles, saying, I want to get rid from the EPC and start something new, which is NFV and SDN based, and maybe I can take some features from the EPC into that, but I want really to get rid of the protocols, the overhead, and all the legacy. They say, I want a new core, which is really IP, NFV, and SDN. EPC is completely IP, but not necessarily NFV and SDN friendly. So that was my summary. These are my takeaways, and I think you want to have your break and you won't have questions, but I leave that to Monica.